Hello everybody. Today we're going to tackle a pretty tough subject called system noise. So let's get started. And of course this is space related. So let's kind of draw a picture of our system up here. Here's the Earth. Let me give myself a little more room. Here's the Earth over here. And it's basically round, and we have a satellite up here. And our satellite is a little CubeSat. And we've got an antenna out here, and it turns out that it's a monopole, which means it radiates equally well or poorly in most all directions. And inside this guy is what we call a low noise amplifier. And we abbreviated that as LNA. And of course this feeds a receiver. Now, if we were to connect a spectrum analyzer to this receiver, that thing produces a display, something similar to this, and on the x-axis is frequency, and on the y-axis is power. Typically in dBm. And if we were to hook that up to our radio at a frequency of interest, we would see some wideband noise out here, and when the signal came on, it would jump up above the noise and come back down. And intuitively, I think we understand is that as the ratio between signal and noise increases, as this gets bigger, the signal-noise ratio, as that gets bigger, that produces a better and better bit error rate. I think that is pretty intuitive. So now let's start to think about, and today this video is going to deal with the noise portion of this signal-to-noise equation. So let's think about the major contributors of noise. It turns out that we have two major contributors. One is the noise coming in on the antenna. And second is we know that all electronics are not perfect, and this amplifier makes noise. Now if the gain of this amplifier is significant, in the range of 15 to 20 dB, it turns out that this is the most controlling factor of everything beyond this point. If we can get this as low as we can with as much gain we can, then the noise generated in subsequent circuits becomes insignificant. So now we need to kind of think about noise. And centuries ago, a guy by the name of Planck, and I think he said something that was obvious, but then he quantified it. He says all the noise, or noise produced by any body in watts, produced by anything that's above absolute zero, the noise can be quantified by some constant, in this case Boltzmann's constant, times its absolute temperature, times the bandwidth of the device that receives it. Right? Now this is a fundamental equation that all communication engineers must know, understand, internalize, memorize, believe, and use. So if you're going to do link, budgets, circuits, anything, this is a very important equation. And it basically says if you know the temperature of the device and you know the bandwidth, and you can go look up Boltzmann's constant, and you can calculate the power produced in watts. All right, now let's relate this to our subject. Is take my word for it that when you have an antenna, the equivalent noise on the antenna is equal to what the antenna is looking at. So in our case, what is it looking at? Well, it's looking at Earth. We know the average temperature of the Earth is about 300 degrees Kelvin, or 290. And of course we got the sun out here, and it is very hot, and we got the galactic background, which is very cold. The black background at the frequencies we're interested in is about 30 degrees Kelvin, maybe cooler, unless you're pointing at some really noisy star. So now here, our antenna is looking in all directions, but it's close to the Earth, and we're just going to guess. We're going to say that the average noise, the average temperature of the antenna is roughly about half of what we see at the Earth, and I've asked the community to help me out and pick a number that's reasonable. So we now know, or we now can calculate the noise that's coming off the antenna. Now we know this guy makes noise, and in our satellite system, we're gonna measure how much noise that makes. Well, it turns out that if you have a lot of money, 100K or so, you can go buy a noise meter. UL is on a little less stringent budget, so we're going to have to do it the hard way. We're gonna measure the noise of this amplifier, and we're going to use the Y method. Go Google that. Go Google that, learn about that. But essentially what we do is we take a known source, we take two known sources. We take a cold source and a hot source, and we make a ratio measurement, and it produces a number called the noise figure. And if it's capitalized, this is expressed in dB. This is the noise figure, which is a ratio, and we typically express that in dB. So now let's get started. I'm going to go to a setup that I have. Let me shift gears here. I have done a little spreadsheet and put some diagrams, if I can get this lit up. And let me shift back to this thing here. Okay, here is my setup. Is that I've got this Hewlett-Packard calibrated noise source, and it puts out two sources, one called a hot source and one called a cold source. And it's feeding our low noise amplifier, which is feeding a spectrum analyzer. So this is our setup here, right? And I didn't quite get moved over enough. Let me shift gears here and slide this over a little bit. And since this guy is made by Hewlett-Packard, now Agilent, it has this formula that the noise figure is this ratio, and this turns out to be the hot and the cold noises. So what we're going to do is we're going to hook this circuit up, and we're going to get two noise figures, one called the T, the temperature of the cold noise, and one called the temperature of the hot source. And since the spreadsheet takes all the pain out of that thing, is that this noise figure here is calculated from this formula right here. And here's what's really nice about spreadsheets is that spreadsheets take all the pain of this thing. This is kind of tough to do, and I'm going to use this equation here. I'm going to use this equation here. I'm going to generate the noise figure off of this equation, and I'm going to use this thing to convert it back to equivalent noise temperature. Now, noise temperature, you can also think of a resistor at some temperature. So if you know how hot this resistor is, you can now know how much power it puts out at the bandwidth you're interested in. So I'm going to take this hot measurement here, and look at my spectrum analyzer and look at the hot measurement. I'm going to take this cold measurement, I'm going to look at it here. I'm going to calculate the noise figure, and then I'm going to convert it to its equivalent temperature. So I've done that. We're testing this unit called 3B and 3A. I made two of these things, and I've run these tests. I've calculated a noise figure, and I've calculated an equivalent noise temperature. Now, so now we go back to our system. As we know the antenna noise, the T sub A. We've seen that was, I think, maybe in this 100 degrees or so, and I've measured the noise temperature of the amplifier, and in the case of the device 3A, that was 87 degrees Kelvin. I can add those up, and this is called the temperature of the system. And what's nice about when you convert things to temperatures, it's a simple addition. So now our system temperature is 187 degrees Kelvin. I can now put that back into this equation. The power that thing is now equal to Boltzmann's constant times the bandwidth. In our case, in our receiver, it's 56 K hertz, and the temperature is 187, and that will calculate what the bandwidth, what the power or the idle noise is. And let me shift back to my spreads. Let me shift my spreadsheet over. So we're going to move it over here. Well, I think I'm going to try to move it over here. So if our total temperature, T subsystem, is 285 degrees, that says that my minimum, my signal standing at the receiver, my idle noise, is minus 126 dBm. So if the noise floor is minus 126, that tells me how much signal I have. Now, what if you don't like this number? What if you say, I just don't like that 126, it's too high? What are the levers that you can pull? Well, it turns out that you only have 3 levers, and one is not very effective. It's the antenna, and it's in a physical environment, and you can't change the temperature of the earth very easy. You can't change the temperature of the sun, and so your antenna is that's not a good lever. But what you can fool with is the noise of this thing. You can reduce it, or you can reduce the bandwidth. That's the only 2 major levers you have to affect the idle noise. So guys, that's it for today. We'll talk about the signals in another video. See you soon.